Just days after 3I/Atlas's closest brush with the Sun, astronomers caught it doing the impossible, drifting miles off course and flashing an intense blue, brighter than comet science predicts. The calculations say it should be shedding billions of tons in debris, yet there's no obvious sign. For the first time, real proof of non-gravitational acceleration has scientists asking, is this the alien technology everyone's feared to find? What happens in December could decide everything. Atlas's journey brought it closest to the Sun on October 29, 2025, at a distance just inside Mars's orbit. But what sets Atlas apart isn't just its origin or timing. The object itself is enormous by interstellar standards. Early estimates put its nucleus between 4 and 7 kilometers across, more than 10 times longer than Oumuamua and several times the size of Borisov. For perspective, if Oumuamua was a ping-pong ball, Atlas would be a multi-story building, looming over everything else in the known interstellar sample. Its speed is just as remarkable, clocking in at around 36 kilometers per second. That's faster than any natural comet of its size ever recorded. The scale and velocity alone make Atlas an outlier among outliers, a visitor whose physical presence is impossible to ignore. Before the anomalies in the headlines, Atlas was already rewriting the limits of what astronomers thought possible for objects entering from deep space. Its size and speed set the stage for every puzzle that followed, raising expectations and tensions about what such a massive interstellar traveler might reveal during its brief encounter with the inner solar system. ALMA's post-perihelion tracking offered a surprise. 3I/Atlas was not where gravity alone predicted. The difference measured about 4 arcseconds, enough to force a closer look at the forces acting on this object. For context, ALMA's typical astrometric accuracy for compact sources is well under half an arcsecond. Here, the team had to account for every known source of error: phase calibration drift, antenna baseline, uncertainties, the motion of Atlas itself across the sky during each integration, and even the effects of solar refraction. Each contribution was modeled and subtracted, with the remaining position shift still far exceeding the combined uncertainties. Cross-checks with independent reduction pipelines, including CASA and Myriad, produced consistent results. The offset was real, not an artifact of software or calibrator error. To strengthen the case, astronomers compared ALMA's data to available optical and space-based astrometry. While instruments like SOHO and stereo confirmed the general trajectory, their pixel scales were too coarse to weigh in on sub-arc-second shifts. No published Gaia or NOEMA results were available yet, but the ALMA offset stood alone as the most precise measurement so far. This displacement isn't just a technicality. In orbital mechanics, even a tiny position error can snowball into major questions about the forces at play. When the observed path diverges from the gravity-only solution, the standard approach is to fit for non-gravitational acceleration terms, parameters known as A1, A2, and A3. For Atlas, the magnitude of the offset demanded a non-zero value for at least one of these terms. The implication, something besides gravity, was nudging the object, and the effect was strong enough to leave a measurable scar on its trajectory. Whether that nudge came from comet-like jets or something less familiar, the data forced a rewrite of the predicted orbit. The next step would be to look for physical evidence of activity that could explain the acceleration, or else confront the possibility of a force with no obvious source. Solar observatories caught 3I/Atlas in the act of something few had anticipated. As the comet rounded the Sun, its brightness didn't just climb, it soared, following a power law close to R to the -7.5. That's a rise so steep it outpaces nearly every known comet, pushing the limits of what outgassing physics can explain. Datasets from Stereo, SOHO, and GOES-19 tracked the light curve in real time, while ground-based telescopes filled in gaps wherever geometry allowed. To make these numbers meaningful, photometry teams calibrated every instrument's response, cross-matched field stars, and corrected for sky background using fixed, physically scaled apertures. The result? A robust measure of how much sunlight Atlas was scattering and emitting as it raced through perihelion. Color told another story. The spectrum shifted blue, noticeably bluer than the Sun itself. Multiband photometry and high-resolution spectroscopy revealed a composite signature, a strong blue continuum from submicron dust overlaid with gas emission bands, especially from CN and C2. Atomic lines of nickel and iron, rare in most comets, stood out in the optical and near-infrared. The color indices and line ratios, checked against models of dust scattering and gas fluorescence, pointed to a coma dominated by gas, not dust, and a dust size distribution skewed toward the tiniest grains. JWST's near-infrared spectra added evidence for complex organics and volatile-rich outbursts, consistent with fresh material being exposed and rapidly vaporized. Translating this brightness into physical terms, the gas production rates and dust scattering models converged on a staggering figure. To generate the observed acceleration, ATLAS should have lost at least 15% of its mass, over 5 billion tons, since before perihelion. Such a loss would normally leave a sprawling debris cloud in its wake, one that should be unmistakable as the comet approaches Earth in December. The numbers, checked and rechecked across teams, set up a high-stakes prediction. Either the debris will be found, confirming a violent natural outburst, or its absence will demand new answers. 9 distinct anomalies now define the 3I/ATLAS case, each flagged not only for its rarity, but for the way it compounds the puzzle. The first is orbital. ATLAS follows a retrograde path, yet its trajectory hugs the ecliptic plane. Out of more than 4,500 catalogued comets, fewer than 10 share this combination, statistically about a 2 in 1,000 occurrence. The second stands out in the realm of comet physics. In mid-2025, telescopes recorded a jet or anti-tail pointing directly at the Sun, defying the usual expectation that cometary tails stream away from solar radiation. Anti-tails themselves are rare, seen in less than 2% of active comets, but persistent sunward jets are almost unheard of. Size and speed together make up the third anomaly. ATLAS measures 4 to 7 kilometers across, but travels at 36 kilometers per second, faster than any comparably large natural object ever recorded. The odds of encountering an interstellar object of this scale and velocity, based on current survey data, fall well below 1 in 1,000. The fourth anomaly is a matter of timing and geometry. ATLAS's perihelion occurred with near-simultaneous alignments to Mars, Venus, and Jupiter, while the Sun's glare made ground-based observation almost impossible. The probability of such a confluence, by current estimates, hovers around 5 in 100,000. Spectroscopy adds a fifth anomaly. Observations from Hubble and the Very Large Telescope revealed a nickel-to-iron ratio higher than 99% of known comets, approaching values seen in engineered alloys. While the precise measurement remains under peer review, the initial data suggest a composition that stands apart from the typical solar system sample. The sixth anomaly concerns water content. Most comets are dominated by water ice, often more than half their mass. ATLAS, according to SOHO and ALMA, contains only about 4% water by mass, placing it among the driest 5% of all measured comets. The seventh anomaly arises from polarization. Photometric studies show ATLAS exhibits extreme negative polarization, values more negative than any natural comet recorded in the past 40 years. Only 3 comets in the modern era have approached this level, and none matched ATLAS's combination of other traits. The eighth anomaly is directional. The object's inbound path lies just 9 degrees from the sky location of the 1977 WOW radio signal, a coincidence found in less than 1% of possible interstellar approach vectors. Finally, the ninth anomaly is photometric. As ATLAS rounded the Sun, its spectrum shifted sharply blue, more so than any active comet previously observed, and with a brightening curve that outpaces standard models of dust and gas-driven activity. Only 2% of comets ever brighten blueward after perihelion, and none as strongly as ATLAS. Each of these anomalies, on its own, might be explainable as an outlier or a rare event. Taken together, they form a checklist of improbabilities that challenge every conventional model, leaving astronomers to weigh whether this is a chain of natural extremes or evidence of something fundamentally new. The arrival of 3I/ATLAS instantly drew comparisons to its 2 famous predecessors, but the similarities end at their interstellar origin. In 2017, astronomers first spotted 1/Oumuamua slicing through the solar system. It was small, somewhere between 100 and 200 meters long, and left no visible coma or tail. Its brightness curve and tumbling motion sparked debates about its shape, with some models favoring a flattened, cigar-like body and others suggesting a pancake. Yet, for all the speculation, Oumuamua remained frustratingly silent. No gas, no dust, no outbursts, and no clear evidence of activity. The object sped away before telescopes could gather more than a handful of data points, leaving behind more questions than answers. 2 years later, I/Borisov entered the scene. Unlike Oumuamua, Borisov behaved like a classic comet, displaying a bright, extended coma and a tail rich in volatile ices. Spectroscopic studies revealed a composition dominated by water, carbon monoxide, and cyanide. Familiar ingredients for a comet, but at concentrations that hinted at a birthplace far from any star. Borisov's nucleus, about a kilometer across, was modest by solar system standards, but massive compared to its predecessor. Its activity, driven by the sublimation of ices, left no doubt. Borisov was a natural, volatile-rich wanderer from another star, behaving much like the comets catalogued closer to home. Atlas doesn't fit either template. Its nucleus dwarfs both earlier visitors, measuring at least 4 kilometers across and possibly as much as 7. That sheer scale, paired with a velocity of 36 kilometers per second, puts it in a class of its own. Yet Atlas refuses to follow the rules set by Borisov or Oumuamua. It is neither inert nor a standard comet. Unlike Oumuamua, Atlas displays clear activity, jets, a coma, and rapid brightening. But unlike Borisov, its composition is strikingly dry, with water making up only a small fraction of its mass. Instead, the coma is dominated by carbon-bearing gases and an unusual abundance of nickel and iron, elements rarely seen at such levels in natural comets. Statistically, the odds of encountering an interstellar object with Atlas's size, speed, and activity profile are vanishingly small. If Oumuamua was the silent drifter and Borisov the familiar wanderer, Atlas is the outlier, a massive, fast intruder showing signs of both comet-like and wholly unfamiliar behavior. Its combination of traits, enormous size, rapid motion, ambiguous activity, and exotic chemistry, places it at a crossroads, defying easy classification. For astronomers, this means every observation carries extra weight, each new measurement a potential clue in understanding not just Atlas, but the broader diversity of interstellar visitors. The urgency now is not just in confirming what Atlas is, but in testing the boundaries of what interstellar objects can be. Claims about 3I/Atlas have triggered a wave of scientific audits and debate across the astronomical community. Every anomaly on the checklist is now under active review, with teams working to verify data quality at every step. The ALMA offset, for example, is being re-examined by independent groups, each reconstructing the astrometric pipeline from raw visibilities to final position fits. Calibration logs, phase reference schemes, and ephemeris files are being cross-checked for overlooked errors. Some teams are even running Monte Carlo simulations, injecting artificial noise to test the robustness of the reported offset. Peer review is ongoing, but incomplete. As of early November, no journal has published a fully quantified error budget for the ALMA measurement. Spectroscopic results, especially those hinting at a high nickel-to-iron ratio, are also under scrutiny. Lab notebooks and calibration software are being audited to trace the chain of custody for every spectrum. Outside labs have been invited to reanalyze the raw data, and sample logs are being made public for transparency. Disagreements over calibration and background subtraction are common, but the process is designed to weed out false positives before any claim becomes consensus. Meanwhile, SETI observatories have kept a close watch for artificial radio emissions, scanning at key frequencies like 1420 MHz. So far, every search has come up empty. No signals, no repeating bursts, nothing to suggest a technological source. The scientific mantra remains: extraordinary claims require extraordinary evidence. Until every anomaly is confirmed and every error accounted for, skepticism is not just encouraged, it is expected. The outcome of December's observations will stand or fall on the strength of this evidence-first approach. December 19, 2025 stands as the moment when every hypothesis about 3/Atlas faces a direct test. On that date, the object will make its closest approach to Earth at roughly 1.8 astronomical units, far from a collision, but close enough for the world's most powerful telescopes to aim every sensor at its path. The checklist is clear. First, the search for a debris cloud. If Atlas's acceleration comes from outgassing, the numbers demand a visible trail. At least 5 billion tons of material, enough to register as a broad, diffuse cloud in deep images. Instruments like ALMA, Hubble, and Gemini South are scheduled for high-cadence monitoring, each capable of detecting faint dust and ice fragments down to a fraction of a percent of the nucleus mass. If the debris appears, it supports the idea of a violent natural outburst. If not, the case for a non-gravitational driver grows stronger, and the so-called 10th anomaly enters the record. Astrometric campaigns will measure Atlas's position with millisecond precision. The target, a predicted deflection of about 0.27 arcseconds from the gravity-only path. ALMA's array, along with Gaia tie-downs and adaptive optics from Keck and VLT, will track the nucleus night after night. Even a subtle offset could confirm ongoing acceleration, while a match with gravitational predictions would tip the scales towards standard physics. Meanwhile, color and polarization teams, some using custom-built polarimeters and hacked CMOS sensors, will watch for any further evolution in the object's spectrum or coma structure. The outcome tree is stark: debris cloud or none, deflection or not. Every anomaly will be checked against the data and every claim will be measured. By the end of December, the world will have answers, either a natural explanation or a new entry in the catalog of cosmic mysteries. On July 1, 2025, the Atlas survey confirmed 3I/Atlas as only the third known interstellar object. After its perihelion on October 29th, ALMA data revealed a 4 arcsecond offset from the predicted position, evidence for non-gravitational acceleration. Solar observatories recorded a rapid, blue-ward brightening, implying at least 5 billion tons of mass loss, yet no debris cloud has been detected so far. 9 documented anomalies now set Atlas apart from both Oumuamua and Borisov, challenging every natural explanation put forward. As December 19th approaches, the global campaign will test whether these anomalies point to outgassing or something unknown. Peer review and data audits continue, and no radio signals or engineered signatures have been confirmed. The true nature of 3I/Atlas remains unresolved, but the decisive evidence, debris or not, will soon be recorded. For now, Atlas stands as the most puzzling interstellar visitor ever documented, and its final test is just days away.